All right, let's just dive right into this explainer. Today, we're looking at how some absolutely cutting-edge data is completely upending, well, pretty much everything we thought we knew about the cosmos.
What if I told you about a planet that literally rains diamonds? Or a magma ocean that somehow holds on to a thick atmosphere? Sounds totally like science fiction, right? But we're looking at actual astronomical discoveries today that are actively breaking the laws of physics as we understand them. We are literally living in this wild era where our telescopes are finally catching up to our most out-there theories.
So here's our cosmic itinerary for this explainer. We're going to hit the impossible planets, our solar system secrets, the edge of space, extreme cosmic physics, and wrap it all up with the next frontier. Let's get to it.
All right, Section 1, the impossible planets, breaking the rules of formation. We're starting with the James Webb Space Telescope, because it is actively finding planets that honestly simply shouldn't exist based on our current scientific models.
It is just fascinating how every single one of these worlds completely defies our models. Take PSR J2322-2650b, for instance. This thing is being squeezed into a literal lemon shape by a rapidly spinning dead star. It has this pure molecular carbon atmosphere where soot clouds drift around, condense, and then it literally rains diamonds. Just mind-blowing. And then you have TOI 5205b. This one is incredibly metal-rich on the inside, but carbon-rich on the outside. Since its interior and exterior aren't mixing at all, it tells us it definitely didn't form the way the gas giants in our own solar system did. Plus, it's this massive Jupiter-sized planet orbiting a tiny star that's just 40% the mass of our sun. That shouldn't even be possible.
And you know, this really brilliantly illustrates just how extreme alien weather can actually be. Here on Earth, we're used to these relatively gentle, continuous cycles of water vapor, right? But contrast that with WASP-94ab. It's a gas giant nearly 700 light-years away. Over there, the intense heat drives this bizarre daily cycle where literal rock-like minerals condense into clouds every single morning, only to just completely vanish by the evening. So the really crucial takeaway about that other rule breaker, TOI 561b, is that it sits at 3,200 degrees Fahrenheit. Now, if it were just a bare rock, which its size and proximity to its star suggests it absolutely should be, it would be searing at 4,900 degrees. This massive temperature drop proves it actually has a thick atmosphere acting as a shield, cooling its day side. And that completely breaks the rule that small, extremely hot planets can't hold onto their atmospheres.
Moving on to Section 2, our solar system secrets. A chaotic neighborhood. Because, well, we don't really have to look hundreds of light-years away to find chaos. Our very own solar system hides an incredibly violent and complex history.
Let's bring it a bit closer to home and see how this shapes our understanding of our planetary neighbors. Computer simulations highlight this wild theory called the Grand Tack. It basically suggests that Jupiter formed way out in the dust disk and then migrated inward, pushing right up to where Mars is today. Then Saturn's gravity essentially yanked it back out. This violent planetary wandering likely cleared out all the raw material around Mars, which, if you think about it, perfectly explains why the red planet is so abnormally small compared to Earth and Venus.
And speaking of Mars, data from NASA's MAVEN orbiter reveals something kind of tragic. The red planet is losing roughly 100 grams of its atmosphere every single second to solar winds. Since Mars lacks a planetary-scale magnetic field to protect it, heavy ions basically plunge into the atmosphere and splash the lighter molecules right out into space. And during solar storms, that escape rate jumps by a factor of 10. It's just getting blasted. Now, this all matters because piecing together our history requires really pristine evidence, like the samples we recently brought back from asteroid Bennu. These samples show that Bennu actually formed 4.5 billion years ago in the deep freeze of the outer solar system. Out there, temperatures plummeted to like minus 400 degrees Fahrenheit. That deep freeze perfectly preserved incredibly high abundances of trapped water, carbon dioxide, and ammonia, which, as you probably know, are the exact molecular ingredients for life. All right, Section 3, the edge of space, beyond the heliosphere. Let's move even further out to the very edges of our solar system, a region that still holds some massive mysteries and pushes our space probes to their absolute limits. It's crazy to think about, but Voyager 2 remains the only spacecraft to have ever visited our distant ice giants. It launched way back in 1977 and discovered that Uranus isn't just gas. It actually hides this vast ocean of water, ammonia, and methane. Then by 1989, it gave us our very first detailed look at that beautiful teal-colored Neptune. Just to give you a sense of the sheer scale here, at 4.5 billion kilometers away, sunlight takes over 4 hours just to reach Neptune. But even beyond the planets, the solar plasma eventually collides head-on with interstellar plasma at what we call the heliopause. Imagine two incredibly fast streams colliding at cosmic speeds. It creates this literal cosmic traffic jam of particles where our sun's protective bubble finally ends and true deep interstellar space actually begins.
And right outside that boundary, that is where the Oort cloud lies. It's this massive, currently theoretical reservoir of comets stretching up to 100,000 astronomical units away. That is almost 2 light-years, meaning it stretches nearly halfway to the next star system. It is just wild to think that this absolute behemoth of a structure in our own backyard is still waiting to be definitively observed.
Moving on to Section 4, Extreme Cosmic Physics. When stars die. Let's completely scale up now to the most violent physics in the universe, what actually happens when massive stars run out of fuel and collapse.
So when a star like our sun dies, nuclear fusion just stops. To avoid collapsing completely under its own immense gravity, it relies entirely on this mind-bending quantum rule, electron degeneracy pressure. Because electrons physically cannot occupy the same state and get too close to each other, they provide this fierce outward push, and that push is literally the only thing holding a dead white dwarf star up.
But theoretical physicists, they push this even further. Using the TOV equation, which was actually developed way back in the 1930s, they can mathematically show that exotic stars could exist with negative pressure. Think about that for a second. If perfectly balanced, this star wouldn't push outward at all. It would exert a constant attractive pull throughout its entire volume. Totally bends the brain, right?
Or, consider the chaotic violence of Wolf-Rayet stars. First spotted back in 1867, their spectral lines show extreme Doppler broadening. Basically, their light signatures are drastically stretched out because the gases in their atmospheres are just moving so erratically. These things are massive ticking time bombs. They are so violently shedding their outer layers that we've only ever found about 500 of them in our entire galaxy. And finally, Section 5, the next frontier, expanding our vision. Because to find more of these incredibly rare phenomena, we're building observatories that will collect and process data at a scale that's, quite frankly, almost unimaginable.
20 terabytes. That is the massive, unbelievable volume of data that the brand new Vera C. Rubin Observatory will process every single night.
By mapping the entire visible southern sky every 3 to 4 nights, this observatory is essentially going to create an ultra-high-definition time-lapse of the universe. We're talking about recording up to 10 million changes in the sky every single night. It'll spot exploding supernovas instantly, track millions of unseen asteroids for planetary defense, and gather absolutely critical data on dark matter and dark energy, which, remember, together make up about 95% of our entire universe.
As the astrophysicist Brian Cox so brilliantly points out, we are currently in this era where our math and our equations predict things way before our telescopes actually catch up. From black holes to those crazy negative pressure stars, the rules of the universe are so beautifully consistent that we can literally just Sherlock Holmes reality.
So, with our instruments looking deeper than ever, what impossible reality are we going to Sherlock Holmes tomorrow? Whether it's a lemon-shaped planet raining diamonds, the preserved icy ingredients for life sitting on some distant asteroid, or the ultimate secrets of dark energy, the universe is just out there waiting. So what do you think we'll discover next?